Thank you so much. So I'm very glad to be here. My name is Loza, as been introduced. Actually, I started here this semester, so this is my second week. Today, I'm going to be talking about machine learning enabled optical methods for live cell and label-free detection. I'm going to tell the story from a perspective of infection diagnostics, bacterial identification. But what I really want you to get is that an approach, an optical method that can be translated for multiple cell types, multiple disease groups, and to see the potential in this integration of machine learning for doing so. Why are we still talking about bacteria in 2023? Because we just learned, if I can go to my next slide, that infectious diseases are still a challenge in our current world. This map shows you sort of the research that was done in response to COVID. Over 3,000 researchers worldwide. 13% of the innovation was also coming from the African continent in response to the pandemic. But one thing it highlights is only 2% of research output increase was shown in infectious disease realm over the past decade before the pandemic. So we can see that we collaborated, but a lot of our efforts was reactive and not proactive. And so global health in general would require a proactive way of doing it. The next challenge we're facing is antibiotic resistance. This is an up and coming one where by 2050, the WHO expects over 10 million lives would be claimed by this issue, compared to what the current mortality load of cancer is. You can see it's pretty high. So among the issues that are resulting in antibiotic resistance is misuse of the antibiotics that we already have. There are several industries that are doing this. I don't know why my slide is going on its own. Okay, there are several industries that are doing this, but healthcare itself is facing the same issue. Part of the reason is, for instance, a bacterial infection in the blood is diagnosed with a long, tedious process, which requires collection of large volumes of blood, where you have few bacteria present in the milliliter of blood, requiring you to culture it over a few days for some bacteria, over several weeks for notoriously slow-growing ones, such as TB. And then to screen for antibiotics, you would need another step of co-incubating with an antibiotic type and looking at the growth of the bacteria. Now, this whole timeline is going to be really long when a patient is presented with, comes to the clinic with signs and symptoms of infection, where the clinician would order generally broad spectrum antibiotics until the results arrive. This leads to nearly half of antibiotics being prescribed either as a wrong dose, a wrong type, or it was not a bacterial infection in the first place. And also the current way of doing antibiotic susceptibility testing, which is outside of the body in culture conditions, is not representative of what's happening in the body. So today I will be discussing a new approach of identifying bacteria types and their antibiotic response using Raman spectroscopy. Now, you may have heard of Raman spectroscopy as a tool for chemical identification, in which you get fingerprints of ethanol, methanol, and different chemical groups widely used in chemistry. We usually do not think of cells as chemicals, but essentially they are made up of chemical building blocks, which are proteins, carbohydrates, lipids, whereby the same principle of using a monochromatic laser light, which is a single color light, to illuminate these chemicals would lead to a scattering effect, where most of the light would be the same color, which we call elastic scattering, some of which will interact with the vibrations in the molecular bonds and lose some of that energy, whereby the scattered light becomes a weaker version, or what we call a Raman shift, which is a shift from your original light wavelength. And we pick this as a spectra, as you see up there, whereby at individual wave numbers, we're looking at what sort of color came out, and it gives you a fingerprint. The hypothesis now is that this fingerprint is unique for the different bacterial types, and also for a single bacteria type when it develops antibiotic resistance over the course of its life. In order to test this hypothesis, we created monolayers of cells and on a gold-coated glass slide as a dried format. And we had an optical setup whereby our laser is focused at about 1 micrometer diffraction limited spot, which essentially gives you one cell at a time acquisition. And so we collected 30 of the most common disease-causing bacterial strains that were found in patients at the Stanford Hospital and looked at their spectra. When you see by eye, most of them look the same. There are a few outliers with peaks that are different from others. But we know there should be nuances in these spectra, which we're not able to identify this way, but a machine learning could be trained and gather this information for us. So to do that, we developed a convolutional neural network, which basically inputs unique spectra from individual cell points. And once it's trained, it will get a new spectra that it has not seen before as a testing set, and it would output probability score of which one of the 30 bacterial types it thinks it is. When we do this, we get this result, which is summarized in this matrix. The columns are the predictions the algorithm are making, and the rows are the true values of what we know from the clinical data. And I want to draw your attention to the diagonal here, where the prediction and the truth are matching. So essentially, that's when it got it right. For individual bacteria types, which includes different species and strains, we are about 82% average accuracy. Again, going back to where we started, which is what is clinically relevant for doing diagnostics, we find that individual bacteria types are not treated with their own antibiotics. The bacteria types can't be grouped into first-line treatment groupings. And when we do just that, we see that the mistakes that are being made are actually classified into one treatment, first-line treatment group. And so when you summarize the results for what could be clinically relevant as a recommendation of drugs, we get about 97% accuracy. In addition, when we look at new data that it has not encountered before as part of the training or the testing set, we're seeing this result. Okay. So in the y-axis is the accuracy of prediction from 70 to 100%. In the x-axis is the number of spectra that was inputted, which is essentially the number of cells. And when you look at the one with the dotted line, it is using the algorithm that was trained in a previous database, completely blinded from the new data set that's coming and how it's performing. And the one in the bold is doing a little bit of fine tuning where we show a few examples of the new group of data set as part of its training before making predictions. Now, if you follow the bold line, after just one bacteria cell, we have about 92% accuracy in classifying. After 10, it is about 99%. And then it plateaus. So this essentially means that we only technically need 1 to 10 cells to make this prediction. And individual spectra is collected at 1 second acquisition time. So you can see how rapid it can be as long as you can isolate these cells from your sample. So the rapid nature is demonstrated here. And also the fact that there are few cells means we can potentially do it without the need for culturing. The second step is looking at what regions of the spectra were actually important to make this classification, right? You can identify these by using what are called feature recognition algorithms, where they would select portions of the input data that were cited or more important to make the classification. And we find that there are about the top 300 data points here, whereby the dark red is the most important, going lighter into the yellow with least importance. And when we only input these 300 features as part of the classification without the entire spectral range, we obtain relatively similar accuracy in the high 90s. So what does this mean? Right now, this data was collected using a scientific grade Raman instrument, which is about 1 inverse centimeter resolution, very expensive, bulky instrument. But you really do not need that resolution, and you don't need the whole range. You can, if you can design a lower cost, more portable version of the spectrometer that targets these bands, you will be able to get pretty much the same accuracy results. In addition, something else we're investigating is correlating this with other fundamental biology studies to identify the molecular origins of the differences. Now, for individual bacteria typing, this may not be as important, but when you think about antibiotic resistance, it sort of gives you information on what sort of bond vibrations were involved and what sort of biomolecular sources were important for that resistance. So the next step, as I mentioned in this process, is identifying the antibiotic response of the bacteria once you know what bacteria it is. And the same principle holds here of using the spectral fingerprint. And when we look at wild type methicillin susceptible and methicillin resistant Staph aureus samples, we get about 90% accuracy at classifying the two, with an area under the curve of about 95%. We went one step further and looked at isogenic pairs. So these are wild type resistant patterns. In the isogenic pairs, we have one mutation that leads to the penicillin binding protein to be different than the ones that are susceptible. And in this case, even we're getting about 82% accuracy. In the interest of time, I have not included additional work that we've done here. Essentially collected 100 E. coli samples of different antibiotic response, and we're able to tell apart the different resistance patterns. We also performed this using TB samples and anti-TB drug resistance, and still holds true. And so essentially the spectral fingerprint hypothesis holds in that we can tell different strains, but also when resistance happens. Now, in my title, I mentioned about live cell. The proof of concept I showed you is on dried samples. And so cells are usually maintained alive in some form of liquid. And also clinical samples are usually blood or urine which are in liquid. So next we tackle the issue of can we do this measurements in liquid effectively to get this result. There are a few challenges doing Raman in liquid, and the two main ones are, one is inefficient light collection because you have to be further away from your sample to accommodate that liquid volume, and then the background signal that comes from other scattering in your liquid media, but also the cover slip and other things that you need to add as part of it. So we demonstrated this in one approach, which can be modified for different purposes into different setups. But in this case, we had glass slide with a liquid well that is made up of a silicon substrate with a double adhesive tape and then a cover slip. Very simple way of translating this. Now, this design was with an eye for a potential low-cost portable setup. And so we also focused on using 10x objective lens with a 0.12 NA light collection efficiency. So we're pretty much testing it to its limit in like the poorest optical setup possible on the Raman instrument. And so we then combined our bacteria and liquid with gold particles to get our signal. Why do we need the gold? Well, I mentioned Raman is specific, but I didn't mention how strong or weak the signal is. Actually, 1 in a million photons scatter inelastically in a Raman fashion, which means your natural Raman signal is extremely low, especially when you have liquid or other solutions around your sample. In the past, scientists have shown that you could use metal structures, also known as plasmonic particles, or dielectric structures such as silicon that can be designed in a nanofabrication film into metasurfaces, both of which are used to tune the light at the nanoscale and magnify it. So these can be made label-free or labeled, but essentially what they can do is enhance the signal up to 8 orders of magnitude or more, which enabled single molecule level identification of Raman signature. And we call this entire method surface enhanced Raman spectroscopy. How do the gold particles enable this enhancement? Well, metals are metals because they have free electrons, and these free electrons essentially like to move when you have an incident light that matches their resonance. So essentially they would dance up and down, and we call these charged particles moving up and down plasmons. And these plasmons can be tuned to move based on the different wavelengths that you send in by changing their size and shape. And so essentially you can have nanoparticles that would interact with different colors of light in the visible or near infrared regions. To identify the best nanoparticle shape for our application, we performed electromagnetic simulation to see how much enhancement we would get. If you have a gold sphere, you'd get about 300 times enhanced signal. The moment you add sharp tips, such as a road shape or some of the fancier star shapes, you get up to 10 to the 5 Raman enhancement, theoretical. And the idea here is that these sharp tips are going to localize the light electromagnetic enhancement into very small surface area, and we in turn call them as hotspots. When you have shapes like a star, you have multiple of these hotspots. So ideally you have more of this enhancement. But when you think about reliably using this as a diagnostic, you want to make sure that you design the same shape every time you're making the synthesis. And this unique star-shaped ones are very difficult to reproduce synthesis after synthesis. However, the nanorods are pretty common, very well established. They still have the same enhancement values, but more reliable in terms of reproducible synthesis. So we moved ahead with those. And you can modify the light color they interact with by changing their aspect ratio, which is their length versus width ratio. So here we made 5 different ones that interact with light of wavelength 660 nanometer up to 850 nanometer in the near infrared. So how do we think about this enhancement in terms of Raman spectroscopy and the light that comes in? Here you see in blue the absorbance, the UV absorbance of your nanorod. So this nanorod absorbs majority from 750-ish up to 970. In theory, if you match your incident light, which is the light that you're using to collect your signal, and the Raman scattered light, which is the shifted light, under this curve, then you should get more enhancement because you're matching the two parameters. And so we went ahead, mixed the nanoparticle with the bacteria. As expected, the bacteria with no nanorods does not show as much signal in the liquid format. Once you have the nanoparticle, you get this boost in signal. We demonstrate that you can do it for multiple different bacteria types. And when you just have the nanoparticle by itself, which is the bottom one here, it doesn't have as much background signal. And essentially, we can also do this over a large area, so 200 by 200 micrometer size in the liquid. And this figure is essentially a color map of that spectra showing that across this large area, we're getting uniform signal. So it's not clamping in one area and not enhancing in the other, which is all good. Then we wanted to see if the theoretical hypothesis of the nanorod's absorbance matching the laser incident light, which is at 785 that we're using here, or the Raman, is valid for our case. So we tested these 3, where the red one matches our Raman signature range, which is between 830 to 930-ish range. The green one, which matches majority of our incident laser light. And the purple one, which is far blue shifted, it doesn't match necessarily the 2 regions of our interest. Surprisingly, we find that the one that is extremely blue shifted, the purple one, performs the best consistently across the different species that we're testing. And so we've looked at this and done several experiments and still getting the same results. And we find in the literature, in liquid Raman studies, the volume that you have plays a part in how the nanoparticles would interact with the light. Essentially, if you have enough volume before the light returns back to your detector and you have nanoparticles there that match the wavelength of light that is moving up or down, they tend to absorb it. And you essentially lose photons in your water volume before it even went to your detector. The ones that are blue shifted do not have this competing interaction. And so effectively, they do better than the ones that are matching. So this is one interesting finding that was not known before in terms of liquid sample for bacteria format. Another one is we found species-specific enhancement performance. Some species had higher photon counts than others. For instance, here the Staph epi has a higher count than E. coli. And when we do cryo-electron microscopy, so we can flash freeze what's happening in the liquid to see how the nanoparticles in gold or cells are interacting, we find that the nanoparticles around the E. coli, which is on the left side there, they are around the nanoparticle, but not necessarily closely bound to the surface. For the Staph epi, every cell seems to be decorated with nanoparticles. Mind you, these nanoparticles are not labeled, they're just swimming in the liquid, but they tend to be attracted to the Staph epi more than the E. coli. And if you're close to the cell within tens of nanometers, that's when you get the highest enhancement. So that's why we're getting this result. When we dug deeper on what interaction might be playing here, we find that our nanorods are positively charged. So when we do zeta potential measurements, they're about 20 millivolts. And these cells are actually generally negatively charged, but not equally so. Staph epi is about 2 orders of magnitude more negatively charged than E. coli is when you look at the charge density over the surface area. So actually, electrostatics and this charge attraction is playing a role in this enhancement. So the main takeaway here is that we can potentially use electrostatics or other physical interactions that are happening without any need for label to maneuver and get enhancement of signal from samples of interest or components of the sample that we're interested in. This is something we're investigating in my lab, both the theory of what sort of interactions are actually important and how much the electrostatics is playing a role around the membrane and the surfactant on the nanoparticle, but also doing experimental studies of different fluidic environments that are leading to this and how we can perturb the system without adding labeling, but unique physical properties to get the enhancement that we want more selectively. So this work was also covered on Physics Today article to see how, enabling the bacteria and natural habitat detection. Now, to tie this up, I want to go back to where I started from, which is the bloodstream infection and clinical diagnostics. I demonstrated we were able to do it in liquid, but how can we scale this to a clinical relevant format, and how can we process the samples that we have? I'm going to pitch here one engineering solution that we have. There could be multiple ways of doing it, but we think this one is more feasible. This one essentially focused on acoustic bioprinting, which is using ultrasound to generate single cellular droplets from volumes of fluid. Idea is you'd have wells that have volumes of blood or other fluid of interest. We would generate individual droplets with cells and nanoparticle mixture, and we'll be able to image this with a large scale Raman setup. And essentially individual pixels in this measurement would be the spectral fingerprint, and our algorithm would output a clinical report of what bacteria was found in that sample and its antibiotic response. Towards this, the acoustic ejection is powerful because you can generate picoliters of volumes without the presence of essentially nozzles. So it makes it a clog-free approach. You can encapsulate individual cells. And also, you can easily multiplex it by having multiple transducers in a large volume. And so essentially, you can process tens of milliliters of volume in fewer minutes than other competing ways of doing it. For instance, microfluidics, which could take longer time to do so. In addition, once the droplet is generated from this free fluid, the cells are viable and they're able to grow on cultures. And we tested it out for bacteria types and blood cells. As you can see here, we repeated our result in that bacteria with nanorods versus not show the same enhancement that we found in a larger volume of cells. We also tested how mixtures are going to give unique results in the spectral fingerprint. So we have a mixture of bacteria with cell and nanorods, different bacteria and everything together. Essentially, what we find is that the spectral fingerprints are unique to the combinations that you have. So in the right, you see the output of the algorithm classification, whereby if you have Staph epi bacteria by itself, E. coli by itself, or RBC by itself, these are unique compared to when you have different combinations of them. So essentially, we have demonstrated that this can be performed on blood sample as well. To summarize, I hope I have convinced you that Raman spectroscopy can be used as a fingerprinting to identify bacteria type, their antibiotic response, and can be performed in liquid sample. And essentially, I would like to broaden this application space to several cell types and be able to monitor live cells, both for therapeutics diagnostics, but also research purposes, where we may be interested in gathering additional dimension of input in our studies of the different cell types. I would like to take a few minutes then to introduce my lab. We're located in the mechanical engineering department here. Our mission is to utilize the nexus of state-of-the-art biomedicine, multimodal sensing, including optics and spectroscopy, and machine learning to meet the unique challenges of diagnostics in extreme environments. Essentially, our tools are going to be optics and spectroscopy based with machine learning as a data analysis and processing tool. And the extreme environments we're referring to include outer space, military, and resource-limited clinical settings. You can think of it as this way. If a diagnostic or a therapeutic can work in space, should work anywhere on Earth, potentially. So we'd like to innovate technologies that are robust enough for anyone, anywhere. The model we follow is based off of the WHO assured criteria, which looks at affordable, sensitive, user-friendly, rapid, robust, equipment-free, and deliverable diagnostic. The same holds true when you think about space, where you have a backpack problem, in the military, when you have a need for robustness in arid conditions. With that, I would like to thank my previous lab and Jen Dion's lab. Most of this work was done there, and everybody that contributed here. I would like to highlight how interdisciplinary this work was. We had, of course, clinicians, engineers, computer scientists, business people looking at how the market is going to be affected by this, and more. And it was an amazing experience, and I would like to model the same things for my lab as well moving forward, and all of the funding agencies. I'd like to thank the current lab members and friends, including collaborators from campus. And we're currently recruiting postdocs and grad students. So if you're interested, please feel free to reach out. And thank you so much for your attention.